Chapter 3 in our Chem 101 course deals with mass relationships in chemical reactions. This is, if you've taken previous chemistry courses in high school or college, what many of you probably called stoichiometry. We want to begin our talks about mathematics and chemistry and about stoichiometry by talking about chemical equations. A chemical equation is a way of writing out what happens in a chemical reaction. On the left side you have reactants, on the right side you have products, and you have the chemical formulas for each. And in order for the law of conservation of mass to be obeyed, to be followed, those chemical equations have to be balanced. So we're going to begin by balancing chemical equations with suitable coefficients. Those are numbers we put before the formula to indicate how many formula units or molecules of each substance are required to get a balanced equation. The number of each atom on each side of the equation has to be the same. And then we'll want to reduce coefficients to the smallest number the smallest possible whole number values. And then check back over your answer, make sure that the numbers you have work. And we'll practice a few of these in class as needed. The first one we want to try is, and you can pause the video now and write this one down, we want to look at propane, which is C3H8. It burns in oxygen. That's your natural gas that you get from your grill is propane. And it burns in oxygen, and the products, if everything goes perfectly, are just carbon dioxide and water vapor. So we'd like you to write a balanced chemical equation for that. And like I said, we'll practice this in class together. Once we have a balanced equation to work with, we can start doing calculations that will tell us how much product we can make from a certain number of grams or liters or other units of a reactant or a group of reactants. In order to do that, we'll have to be able to calculate molecular mass, or formula mass for the case of ionic compounds, and those are basically the sums of the masses of all of the atoms in the formula of that compound, whether we're looking at a molecular compound or an ionic compound. What this gives us is the number of grams in a mole of that compound, where a mole is 6.022 times 10 to the 23rd molecules, or formula units, or atoms, or whatever it is that we're looking at. Sugar, blood sugar, is glucose. Fructose actually has the same formula. So again, pause the video, try this out on your own, and we'll try it in class together. Calculate the molar mass, or what your book calls molecular weight. I don't care if we're using weight at that point, but the molar mass or molecular mass of glucose, C6H12O6. If your number is less than 100 or greater than 200, you're doing something wrong. So I'll give you that as a hint, but we'll work this one out together in class. And once we've done that, we should be able to use dimensional analysis to calculate how many moles of glucose there would be in 2 grams. I'll give you a hint. It is less than a mole. In fact, it is less than 1/10 of a mole. Once we can do this, we can solve problems like this one here, which again I'd like you to try on your own, and we'll work it together when we meet. Aqueous solution of sodium hypochlorite, that's NaOCl, we also call it bleach, is made by reacting sodium hydroxide with chlorine gas. So the question is, how many grams of sodium hydroxide will we need to react with 25 grams of chlorine gas? So we have the formulas right there, and we can write a balanced chemical equation for that reaction. And some of you probably just noticed a little blip in the video where I repaired a typographical error right here and right here. So now we have a properly balanced chemical equation for this reaction. And once we know this, we'll use dimensional analysis to calculate how many moles of chlorine gas this is. So chlorine atoms have a molar mass of 35.453 grams per mole. So chlorine molecule has a molar mass of 70.906 grams per mole. So we can use that to figure out how many moles of chlorine gas we have. We're going to use 2 moles of NaOH for every 1 mole of chlorine gas. So if we calculate how many moles of chlorine gas we need twice that many moles of sodium hydroxide, and then we can use the molar mass of sodium hydroxide to calculate how many grams that is, and we'll do that together in class. I just gave you some hints on how to work that. I'd like as many of you as possible to have that one done by the next time that we meet. Once we know how much product we expect to get based on the reactants that we started with, that'll be our theoretical yield, what we calculated, what we expected. However, experiments don't always go exactly as planned. So if we can calculate the theoretical yield and then do the experiment in the lab and get an actual yield, we can calculate the percent yield, what percent of what we expected that we actually got, and it's just the actual over the theoretical, and then multiply that fraction by 100 to make it a percent. The other thing that can happen sometimes is we can have more than we need of one reactant to react with the amount that we have of the other. For example, if we wanted to make cheap bologna sandwiches to hand out at some sort of a function, we could make each bologna sandwich with 2 pieces of bread and 1 piece of bologna. And if we had 5,000 pieces of bread and 100 pieces of bologna, we could only make 100 sandwiches. We'd have a lot of leftover bread. So the limiting reactant in that problem was the bologna. We only had enough bologna to make 100 sandwiches, but we had enough bread to make 2,500 sandwiches, but we couldn't make them because we didn't have the bologna. So we'll be able to figure out, by doing those kinds of calculations, using molar masses, using balanced equations, what the limiting reactant and what the excess reactant is in a particular problem. And an example of that, cisplatin, which is PT-NH3-2-Cl2, is an important anti-cancer agent used in treatment of certain kinds of tumors. And we can make it by reacting ammonia with potassium tetrachloroplatinate. So here's tetrachloroplatinate. That's a polyatomic ion. It's much more complicated than we'll usually handle in the course. Don't expect you to have that one memorized. It is a 2- ion, so 2 potassiums for each. If this is the balanced chemical equation then, and we have 10 grams each of our reactants, how much product can we make? How much of this cancer-causing drug can we, how much of this cancer-relieving drug can we make? And the answer to that question is going to be arrived at by doing the problem twice. We're going to do the problem calculating how much platinum we could make, how much cisplatin we could make from the 10 grams of ammonia, assuming we had more than we needed of the other reactant, and then we will calculate that based on potassium tetrachloroplatinate, assuming we had enough of the ammonia. And just like we did in the bologna problem, whichever one of those gives us the smallest answer, we will assume is the correct answer. Because we had enough bologna to make 100 sandwiches, we had enough bread to make 2,500, we can only make 100. And we'll do that same calculation in class together as a worked example before we do any assignments on this chapter. Once we know that, we can back calculate how much of the excess reactant got used up and subtract from the original amount, figure out how much is going to be left over, how much excess reactant we have. And so we'll work that problem together as well. Another way that we can look at formulas is if we have a compound whose formula we don't know, we can figure out what compound we have by doing a mass analysis on that compound, by taking it to an instrument that can analyze that compound and find out what percent of that compound is made up of each element in the compound, and that's its percent composition. That can be done by an element analysis, which just gives us the exact percentages, or by combustion analysis, which gives us a little bit more calculation to do. But the empirical formula of a compound then is the formula that gives the ratio of the atoms in the chemical compound. Now, compound we talked about earlier, sugar, glucose, C6H12O6. The empirical formula for that compound is CH2O. Because there's 6 carbons on each molecule, there's 6 oxygens, that's a 1-to-1 ratio. And there's twice that many hydrogens, 2-to-1 ratio. So the empirical formula is CH2O, but the molecular formula is 6 times that large. Excuse me, I just removed a line that I had left from an old lecture by accident, so you can ignore that thing that flashed up there and disappeared. Now, this is a really neat problem that I'm actually looking forward to working out with you guys. Caproic acid is what you smell if you smell a goat that hasn't been washed, a smelly old goat, or a pair of dirty socks that have been left in the gym locker for too long. That particular odor is made by a compound called caproic acid. That compound has carbon, hydrogen, and oxygen on it. If we analyze that by combustion analysis, we get 0.418 grams of carbon dioxide. So we should be able to calculate how many moles of carbon that is. And 1.023 grams of hydrogen. Of water, we can calculate how many moles of hydrogen atoms are involved in that. And then, if we add up these numbers and subtract from 0.45, we'll realize how much extra oxygen has been added by the combustion, and we could subtract that out, find out how much oxygen was in the original compound, and calculate that in moles, and we'll get an empirical formula for caproic acid. And then if we know the molar mass of caproic acid, we can figure out the molecular formula. For example, if we get a quarter of this number as the molar mass of our empirical formula, then we'll quadruple that to get the molar mass, to get the actual molecular formula. So these are all problems that we're going to work together. Something you'll notice, not a lot of theory in this chapter. We got the whole chapter's lecture done in under 15 minutes. But a lot of math work to be done, and this is a very important chapter. A lot of the things that we do over the rest of this course and next semester, and for you chem majors for really the rest of your career, are going to build on what we do this chapter. So when we work these problems together in class, pay close attention. When you try these homework problems, after we've worked those problems together in class, if you start having a lot of trouble with them, that is a time to make sure that you get some extra help from me or from a tutor or from someone in the extra help sessions that I told you about recently. So have fun trying these out, and I will see you in class next time.